Hi everybody, welcome back. In the last video, we went through a number of examples involving spherically symmetric charge distributions, where we used Gauss's law to solve for the electric field at arbitrary positions away from spherically symmetric charge distributions, or within spherically symmetric charge distributions. Working up to the last example, where we had a continuous charge distribution that was non-uniform, but still exhibited the spherical symmetry. In this video, we're going to turn our attention to planar symmetry, situations where, for example, your charge distribution will not have a functional dependence on xy, but it might have a functional dependence on z, if we're thinking about the traditional three-dimensional Cartesian plane xyz. So let's turn our attention to an example of an infinite sheet of constant charge density eta. So determine the electric field strength above and below the sheet. What we're going to do is we're going to create a Gaussian pillbox. A lot of people like to use circles as their edges, or at least as the tops and bottoms of their imaginary Gaussian surfaces in these examples. I'm intentionally going to make this a weirdly shaped pillbox to drive home the point that it really does not matter what shape you use when you're dealing with planar symmetry, for reasons that will soon become apparent. So here I have a thin sheet of charge with charge density eta, and I have a Gaussian pillbox. The idea is that above this thing I have a surface that's above my sheet, and at the same distance below the sheet I also have the surface underneath. So we don't, as it turns out, it doesn't matter what the thickness of our Gaussian surface is, because as long as we have it one end the same distance above the sheet and the other end the same distance below the sheet, it really just won't matter. The thickness does not show up in the amount of charge contained. The amount of charge contained is proportional to the area that you see here of one of our top or bottom surfaces. Now, in this particular example, it doesn't even matter whether the top surface is the same distance above the sheet as the bottom surface is below it, but in future examples it often will, and that's why we're going to adopt the practice of that sort of symmetry right now, that we're at a certain fixed distance plus or minus z from the sheet, which is assumed to be at z equals 0, but it's infinite in distribution in the xy plane. So if eta was not constant, this wouldn't work. As long as eta is constant, the electric field is going to be coming out perpendicular to the sheet, which means it's going to be parallel to the sides of our Gaussian surface here. But if we did not have this planar symmetry, if eta wasn't constant, then the electric field would not necessarily be tangent to the sides of our Gaussian surface, and we wouldn't be able to use Gauss's law. So, well, here's the thing. This is actually a trivial example, because the flux going through the top of our sheet, the flux from the sheet of charge going through the top of our Gaussian surface is simply equal to E times A. Integral of E vector dot dA vector, well, the electric field's constant at a particular height. In fact, it turns out, as you're going to see, at all heights, and the area of our surface at the top is A. Well, you're also going to have the same thing at the bottom surface. In other words, assuming that this is a positive charge distribution, the electric field will be pointed downward below the sheet, and it's going to be pointed in the same direction as the unit normal vector for the area of the surface below the sheet. So we get an EA from the top, we get an EA at the bottom. So the total flux through our imaginary Gaussian surface is 2EA. Oh gosh, I don't know what A is. What am I ever going to do? You'll see, it's going to go away. Okay, so there's our flux, the left side of Gauss's law. What about the right side of Gauss's law? Well, here it is. I told you this one was trivial. The amount of charge enclosed is simply equal to, well, the integral of eta dA, but eta's constant. Eta pops out. So we're just going to be left with the integral of dA. Well, that's called A. So the enclosed charge is just eta times A. So the left side of Gauss's law is 2EA. The right side of Gauss's law is eta A over epsilon naught. Yeah, don't forget that epsilon naught. Lots of people do. So we have 2EA equals e to a over epsilon naught. And look at that, the areas cancel. It doesn't matter what the area of our Gaussian surface was. It doesn't matter how it was shaped, as long as the edges are perpendicular to the plane of the sheet. So overall, we get that the electric field is eta over 2 epsilon naught. That's the electric field strength. Now, the electric field vector would be eta over 2 epsilon naught times plus or minus k, where k is our unit vector in the z direction. And I used a fancy way of writing that plus or minus as z over the absolute value of z. So that if z is positive, we just get plus. If z is negative, we end up getting a minus. Okay, so that's what it is for a sheet. What if we have capacitor plates? In other words, two sheets. One of the sheets has a positive charge, and the other sheet has a negative charge. And the sheets are separated by a distance d. So we're going to assume that the dimension of our capacitor plates is much larger than the separation distance d. In other words, when we say much larger, what we really mean is that our sheets are infinite, effectively. Well, we're going to assume the capacitor plates are infinite in extent. Well, the actual area A naught and the distance between the plates is irrelevant. That's what our last example just told us. In other words, if you look back at the last example, you see that there is no real z dependence here, at least in the electric field strength. And even in the electric field vector, it's only about the direction. And the direction we can take into account geometrically. So we're going to use the result that we got for the single plate. Well, assuming the positively charged plate is on the top, then above that, the electric field is going to be positive. But wait a second, superposition principle. If the negatively charged plate is at the bottom, then above both plates, the negatively charged plate is going to give us a negative electric field. The positively charged plate will give us a positive electric field of the same strength. They're going to cancel. Same thing is going to happen if you are below both plates. The negative plate is going to have an electric field pointing up. The positive plate farther above is going to have an electric field pointing down. Those are going to cancel. What matters is in the middle. In the middle, if the positive plate is at the top, then the electric field due to the top plate is going to be down. The electric field due to the bottom plate, which is negative, is also going to be down, and things are going to add together. So you get an eta over 2 epsilon naught, which is negative, minus another eta over 2 epsilon naught. That just gives you negative eta over epsilon naught. So you find that the field strength between the plates is eta over epsilon naught. That's something that I would recommend memorizing, that the electric field between the plates of a capacitor is equal to the charge density over epsilon naught. So quite important to think of later on. Lots of multiple choice questions come up on the AP exam with this. And as we mentioned, above both plates or below both plates, the electric fields end up canceling. So this is an important result. For a parallel plate capacitor, something that we're going to be dealing with a lot in future units, where it's assumed that the area of each plate is huge compared with the separation between the plates, then that tells us that the electric field between the plates is always eta over epsilon naught, and the electric field outside of the plates is 0. And that's something that we can see in this depiction. So on the right side is really our idealized situation that we just discussed, and you see that outside of the plates the electric fields end up canceling because, say you have plate 1 on the left positively charged, plate 2 on the right negatively charged. Well, there's the contribution from plate 1, there's the contribution from plate 2. Remember that these plates are large enough that due to Gauss's law that we used before, there is no distance dependence. There is no z dependence. In this case, comparing with our last example, we're having the z-axis going toward the left. But in between the plates, everything adds together, and you get a strong electric field there. Now, in the real situation, where you have finite-sized plates, you have what we call edge effects, where the electric field kind of bows out away from the plates themselves, and you end up having a very weak electric field on the outside near the plates. But by very weak, we mean much weaker than the electric field inside of the plates. This is something that you can also verify using the charges and field simulation by PhET, which is a great way of getting some intuitive understanding of these types of charge distributions. Let's take a look at another example involving planar symmetry. This is a slab example. This type of problem does occasionally show up on the AP exam. In fact, this particular example, I believe, I have seen on the AP exam. So here, we're going to have a charge distribution such that it's at a maximum in the center of a slab that is centered in the XY plane, such that the center of it is at z equals 0. And goes down to 0 at the edge of the slab. So the slab has a thickness of 2a. So a above the xy plane, a below the xy plane, so that the charge density goes to 0 at the edge of the slab. So again, we're going to create a Gaussian pillbox of area A, where the area is parallel to the slab surface. This will be the case both inside and outside of the slab. So I stole this picture from your textbook, the Knight 2013 textbook, Physics for Scientists and Engineers, 3rd edition. And here we have our Gaussian, our imaginary Gaussian surface. So outside of the slab, it simply contains the charge equal to whatever's in here, whereas inside of the slab, the contained charge is less. But we're going to need to figure out what the contained charge is. Well, to figure out what the contained charge is outside of the slab, we're going to integrate from z equals 0 out to z equals a. And inside of the slab, we're going to integrate from z prime equals 0 out to z prime equals z. And in each case, we're going to multiply by 2 because we've got to take into account the situation both above and below the slab. So, again, for our purposes, it really doesn't matter what the shape of our pillbox is. It also doesn't matter what the area is, whether it's A or dA. We're just going to call it A. And the nice thing, again, about planar symmetry is you can make the shape anything you want. So, let's see how it goes. The left side, integral of E vector dot dA vector. Well, that's easy. 2EA, just like before. That's the thing about these Gauss's law problems. The left side of the integral is always exactly the same for a given type of symmetry. For spherical symmetry, it's always E times 4 pi r squared. For planar symmetry, it's always 2EA every time. That's something to keep in mind. Now, as we mentioned, the right side of this is where all of the fun's going to arise. So let's see how that goes. Well, we know what rho is. They told us. Now, how much charge is involved in a little bitty piece of thickness dz? Well, that's going to be given by rho times a times the thickness. So rho a dz. So there we go. Now we know what dq is. So the enclosed charge is equal to the sum of all of the little bitty dq's. And what we're going to do, instead of integrating from z prime equals negative z to positive z, we're going to go, as I mentioned before, from 0 to z and just multiply by 2. And exploit the fact that we have this symmetry about the xy plane. So we plug in what rho is. It's rho naught times 1 minus z prime over a, and here I got rid of the absolute value bar since I'm just integrating for positive z's. And that's a trivial integral. You did that back in kindergarten calculus. So the 1 just integrates as a z prime. The z prime over a becomes a z prime squared over 2a. And remember, inside of the slab, we're going from 0 to z, where z is less than or equal to a, where 2a is the thickness of the slab. So upon doing that, we find that the charge enclosed in our imaginary Gaussian surface of thickness 2z, remember we exploited some symmetry here, there's the factor of 2, is equal to 2a rho naught times z minus z squared over 2a. So that's the amount of charge that's enclosed. That's the part most of the right side of Gauss's law. Again, don't forget to divide that by epsilon naught. The left side is 2EA, and just like in our prior example, the A's cancel. The A's will always cancel if you've done Gauss's law right for planar symmetry. The 2's also cancel in this example. So that just leaves E alone, and we have rho naught over epsilon naught times Z over Z squared over 2A. As long as as long as Z is between 0 and A, or as long as 2Z is between negative A and A. Or actually, I should really say as long as plus or minus Z is between negative A and A. So there it is inside of the slab, all the way out to the edge of the slab. So if Z is equal to A, then you end up just getting an A minus an A squared over 2A, or just A over 2 times a rho naught over epsilon naught at the surface. But what about if you're outside of the surface? Well, I just hinted at that, because outside of the surface, the amount of charge is going to be the same as the amount of charge enclosed when you have just only the stuff inside, out to the edge of the sphere, or sorry, out to the edge of the slab. Now, unfortunately, there is an errant factor of epsilon naught here, because I copied this from the electric field. So we need to get rid of that errant factor of epsilon naught. So I'm going to say fix it. And just like that, it's fixed. Notice it also gave me back this factor of 2 that I had forgotten, because if you go back to the previous result, the enclosed charge is like this, and there's that factor of 2 that's there. So now, overall, setting this last result equal to 2EA, the A's cancel, divide by 2, and you get rho naught A over 2 epsilon naught for the electric field. Again, don't forget to divide your enclosed charge by epsilon naught. So there is the electric field for this particular slab of charge. So note that when you're calculating the enclosed charge, the volume element for planar symmetry is A dz, where, assuming that you're in the xy plane, and the A is the same A that you have in that flux, where each side gives you a flux of EA for a total flux of 2EA. And the A's will always cancel in the end. Now, you might think about a comparison with our spherical symmetry problems. In this case, our rho naught didn't go away. In the spherical symmetry in the previous video, our rho naught went away. Well, that's because in the spherical symmetry, we were told what the total charge was, and we had to come up with this normalization constant rho naught. Here, we were given rho naught as just one of the givens in the problem, so our answer was left in those terms. So if they had told us the charge on the sphere, we would have been able to calculate rho naught. In this case, they gave us rho naught and said, call it rho naught. So that's the end of our discussion about planar symmetry. In the next video, we will discuss cylindrical symmetry, how to apply Gauss's law to solve for the electric field in problems involving cylindrical symmetry. So until then, questions and comments on YouTube, and thank you for watching.